So thank you very much for attending this course. My name is Fabio Di Trapani. I'm from Politecnico di Torino. Today, for this afternoon in this summer school, we will focus on some very important topics in the to get started with Opensees. So we'll start focusing on analysis, and in particular, nonlinear static analysis with concentrated plasticity approach and with the distributed plasticity approach. I would like to ask you if everyone has received the material. I mean, we have 3 presentations. One is related to the theoretical aspects, and the other 2 are basically exercises. Then I have uploaded some Python scripts that are the scripts of the exercise that we are going to do. So you were able to open these, they are in a zip folder, in a WinRAR folder. You could find it? Okay, that's very good. Okay, basically, but it is a very basic introduction. Structural analysis methods are maybe linear static or linear dynamic, or nonlinear methods. So basically on what you are more interested in, or the complexity of the assessment that you have to do for your structure. So you can go with a linear or nonlinear analysis method that can be linear static, linear dynamic, nonlinear static, or nonlinear dynamic. The very big difference between a linear problem and a nonlinear problem, we are not getting into details, just to make the main difference is that in a nonlinear model, the solution is given in one step. So the model is totally elastic, the material is elastic, and the elements are elastic beam or column elements. So you will get the generalized displacement by a simple step. So by the inversion of the stiffness matrix, you will get immediately the generalized displacement, and from the displacements you can get the internal forces of the structure. So this is very fast, and it is lower from the computational point of view. On the other hand, we cannot assess, as you can imagine, the post-elastic response of the structure. And these methods are generally more conservative, provide more conservative results. If you want to go into the nonlinear field, your model should account for the inelastic response of the material. So, and the elements that compose your structural model should be made of elements or sections that can account from the material getting into the nonlinear response. In the case of after the elastic stage, so then you can have monotonic behavior in the case in which you are going for a pushover analysis, for example, or in the case if you want to go with a cyclic or a dynamic analysis, you also have to define the hysteretic response. To study the behavior of frame structures, the mostly common models that we have, starting from the older one, the concentrated plasticity approach, and the most recent, but we talk about 20 years of use of fiber section based model, meaning distributed plasticity approach. In the first part of this lecture, we will focus on the classic approach of using plastic hinges to model the plasticity into frame elements. As regards the solution of a nonlinear problem, just very briefly, why this is different with respect to an elastic problems. The very big difference is here. So instead of having a single step in which you can just invert the stiffness matrix to get a generalized displacement, you have to do multiple steps. So you have to provide some increments, and after the increment with the initial stiffness, you get the displacement by basically dividing the force by the initial stiffness, and based on this displacement, you compute the structural response of, that is what you can call element state determination, structure state determination up to the material state determination. You get the structural response, and you compute the residual that is called unbalance also. If this residual is lower than the tolerance, if is larger than the admitted tolerance, then you can go with a reduced stiffness until the tolerance is the difference is lower than the tolerance. And this computation, for it's obvious that this kind of computing the different points of the nonlinear curve takes much more time, because instead of having just the solution in one step, you have different steps, and between the different steps, you have multiple iterations. Because of this, when you go into a linear model, there is a matter of time, and you have to be aware of the model that you're using. In these very famous pictures, the most common used models to model inelasticity in frame member are represented. Going from the widely used concept of plastic hinge or nonlinear spring to the very, very detailed finite element continuum model. These are models like Abacus or also Opensees, but working with 3D brick elements. In the middle, between the elements with concentrated plasticity and the continuum modeling, this most recent class of materials that is called the distributed plasticity elements is going to be used very frequently, especially from the Opensees users. But let's talk about concentrated plasticity approach from a conceptual point of view. Concentrated plasticity approach provides concentrating the region when it is expected to experience plasticity in a few points. For example, if this is a frame element, and for these two forces, you expect that the bending moment diagram is like the one that you have in the in the case of flexural demand, the maximum of the moments are in general at the ends of the beams and of the core. So it is expected that the plastic hinge may form in this region. Okay. Okay. Can you hear me better? Okay. 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 In this case, we are not going by determining the moment, the inelastic response from equilibrium condition, from mechanical condition, but we are assigning an empirical moment, rotation, relationship, in this case for the flexural case, to these hinges. By doing a very classic example of a cantilever beam in reinforced concrete. In this case, you can assume, for example, that in the elastic case, the curvature is basically the moment divided the elastic moment and the elastic modulus and the moment of inertia. By applying this force, if you have that the moment diagram is linear, as you say, but by assuming that you have some hardening, so when you get the maximum, the yielding moment here, when you get the yielding moment here, then you have some hardening of the material. Let's say that is steel, this steel. This is theta y. This is the ultimate rotation. It means that you can increase the moment after beyond the yielding point to the ultimate moment, okay? And this means that in the space between, in the region between the yielding moment and the ultimate moment, all the fibers are getting totally plasticized. And because of this, you have a variable trend of this EJ product, okay? Because if you are in an elastic stage, the EJ is constant. So if you go to, if you draw the curvature diagram, this curvature diagram is linear too. But when you have cracks or when you have plasticity in the steel, you start having peaks of these. You have sudden reduction of the product EJ and large increases of the curvature. Because of this, we are used to call this region where this sudden increase of curvature occurs as a plastic hinge. In the idealization of the plastic hinge model is based on the concept of converting the moment curvature response in the cross-section interested from the plasticization to a moment rotation curve. In this moment rotation curve, it is very easy to be applied as a mechanical relationship, for example, to your software, in which you know when you get the yielding moment, the slope of your relationship changes until ultimate rotation that, for example, you are going to compute. This can be done by setting simple equilibrium conditions. For example, we can set that for getting the ultimate curvature is basically obtained when, for a reinforced concrete cross-section, when we achieve the ultimate straining compression, and we can evaluate, in this case, the ultimate moment and the ultimate curvature, and these values are here and here. In the case in which we want to evaluate the yielding curvature, we just block this point, so we make a picture of what is happening when the yielding strain is obtained. Then you set the equilibrium and get yielding moment and yielding curvature. And this is the very simple way, as you know, to get a moment curvature diagram. But the moment curvature diagram is, as we said, related to the cross-section only. If I want to move from a moment curvature diagram to a moment rotation diagram, that is the one that I have to implement to get a moment rotation relationship to my structural model, I need to integrate the curvature, especially along the region where the major plasticity occurs. There are, in the literature, some methods that provide directly, especially for reinforced concrete columns, that provide relevant values of chord rotation at yielding and the ultimate chord rotation. To do this, some parameters that are very important to define are, for example, the so-called chord rotation. And the chord rotation is basically the angle joining between the undeformed line of the structural axis, so this one, and the line connecting the extremal joints, this and this. So I'm gonna call this angle chord rotation. That is a typical global parameter that is used to define, that we will use to define our relationship in terms of plasticity, okay? In this case, the term called LV, shear span, plays a relevant role. Basically, the shear span is the ratio, is the distance between the end of the beam and the null moment point. So in this case of the cantilever beam, the LV is coincided with the entire length. But if you consider, for example, a double fixed beam like this, the distance between the end of the beam and the null point of the moment diagram, in this case, is L of L. So basically, based on the constraint condition at the end of the beams, we have different definition of the shear span. And finally, I'm telling you this information because they are important to define the expression of the ultimate chord rotation and the yielding chord rotation. The total chord rotation of the ultimate chord rotation of the structural member can be decoupled in two parts. There is an elastic part that we will call theta y, and a plastic part that we call theta plastic. And they are necessary to be computed to finalize the determination of our moment rotation curve. In the hypothesis that the plastic rotation remains constant in the plastic hinge region, okay, we can simply obtain the total, the plastic rotation as, this is the plastic curvature, this is the plastic curvature, phi p, since it is constant in this region, by multiplying this to the length of the plastic hinge, we will get the plastic rotation. The plastic rotation summed to the yielding rotation will provide us the ultimate rotation. That is the principle of this expression that you can find, for example, in the Eurocode 8. That is a mechanical base model. So basically, this is saying that when you do your moment curvature analysis, phi u and phi y, by multiplying your moment curvature, the difference of the moment curvature by the length of the plastic hinge, so you can get the plastic rotation. And inside this expression, we have some relevant quantities that we have defined previously. So the shear span and the length of the plastic hinge. The yielding rotation is again obtained by this semi-empirical equation that is proposed by Eurocode 8. for reinforced concrete cross-section. Then we have this expression for the determination of the plastic hinge length. So the procedure is the following. First, I compute the moment curvature diagram for my cross-section. With phi u and phi y. Then I evaluate the plastic hinge length, the shear span of the case, and based on this data, I can evaluate theta u and theta y. And so I can realize my mechanical model that I can introduce, for example, as a nonlinear spring is M theta model that I can set into as a nonlinear spring to be used in Opensees, for example. That is what you see in this diagram. So what we are basically representing here, or what was talking about, is what is the best way of defining, what is the way of defining this nonlinear relationship that is a relationship between 2 points, that these 2 points have the same coordinates. Between these 2 points, I give a nonlinear relationship between the, for example, in this case, the moments and the rotation. If I want to do a sample modeling of a frame, for example, in which I expect that the plastic hinge can perform at the end of the elements, I have to duplicate the nodes. So I'm not going here with node 1, but I have to set node 1 and another couplet node. These 2 nodes should be constrained together along the horizontal and the vertical direction. And they have a special relationship that is, for example, this nonlinear relationship between them. So basically, this realizes a hinge with a nonlinear spring that provides my inelastic relationship. Okay? Of course, you can tell me, yes, but you have interaction with the axial force that may change the response of this moment rotation curve. And some softwares and some concentrated plasticity model can implement also this response, this interaction between the axial force and the bending moment response, because as you commonly know, the increase in the axial force on the element will increase the flexural response, but will reduce the ductility. So it is important also by using, that is not our case, but you will find in some cases the need for defining multiple moment rotation curve, so that if during your analysis your axial force is changing, I make an example. Let's say that this is your structure, very simple structures. You are increasing the force here. You have that this element is getting decompression, and this element is getting more compressed because of this analysis. So let's focus on this element. So it starts with an axial force that is N0. During the analysis, I'm changing the level of the axial force step by step. So it means that its capacity as chord rotation will change based on the axial force. In this case, if I think that PM interaction is relevant, I should use PM interaction hinges. In other cases, the fixed moment rotation relationship is assumed. For example, this is made by assuming an average level of axial force. Possible combination in the case of concentrated plasticity. For example, I may want to evaluate not only the inelastic flexural response, but also the inelastic shear response. So let's say that I have some shear capacity, shear limitation for this element. So this is my force that is applied here, okay? Let's say that in the first case, we assume that the shear capacity, the maximum shear capacity of the element is this one, okay? So I can apply the lateral force, I can apply this lateral force, and I'm not reaching in any case the value of the maximum shear, okay? So in this case, the flexural response is complete. This is the flexural response. But let's say that my structural member has a shear limitation. So I want to model the fact that during the analysis, the element is failing in shear. So assuming in this second case that the shear capacity is lower than the capacity that the maximum capacity that they can develop under flexural condition. So in this case, I should model a second behavior. So for example, I can introduce a new concentrated plasticity model. In this case, it is a V delta model that regulates the relationship between the shear that I'm experiencing at the base of this column and the relative displacement between these two nodes, okay? In this case, and this is the relationship, okay? In this case, if the shear is exceeded, I will no longer experience this diagram, but I can model the brittle failure because of shear collapse of the element. So this is just to say that the concentrated plasticity approach is not only related to flexural plastic hinge. I can combine flexural plastic hinge that relate moment and rotation to other hinges, for example, shear and relative displacement, or simulate other phenomena. In this case, this is very useful. Also, this kind of approach of using a concentrated hinge is used combined with distributed plasticity, because in the distributed plasticity approach, we can model only the shear response, the flexural response, but we don't account for the shear. So sometimes it's useful also to use a shear hinge in the case we have shear sensitive problems. Okay, before going to the exercise that I want to show, this was an introduction, just a very brief introduction. Of course, these topics, most of you are expert this topic. This just was a brief recall. Concentrated plasticity is the most classic approach that we have to model plasticity. It is widely used and it is convenient. It's stable from the computational point of view. Differently on what we will see with respect to the distributed plasticity approach, the plastic hinge needs to be calibrated. What means need to be calibrated? That hinge by hinge, I have to evaluate this relationship, this moment rotation relationship, and this moment rotation relationship is based on the geometry of the cross-section, on the materials, and on the axial force level, and on the reinforcement for sure. So hinge by hinge, I have to do a fiber section analysis. A moment curvature analysis of the cross section and determine the relevant chord rotation values. In this way, I'm calibrating the hinges in my model and I'm positioning the hinges where I need in my model. And so they can activate in the case of exceeding the yielding forces of deformation, okay? Another concept that is important is the axial force and bending moment interaction. This is very important. If I use a M theta hinge, simple M theta hinge, I'm not taking into account the variability of the response of the hinge based on the variation of the axial load. So I may want to account or not account. I should consider if this is relevant to my problem. And the reliability of this model, for sure, depends on the reliability of the model that I'm using to calibrate the hinge. So, for example, this formula, this is a formula. This is another formula. This is an empirical formula of the Eurocode date. This is a semi-empirical formula, but these formula are based on data in this case. So as you can see, this is the dispersion that you have by using this formula to evaluate the yielding rotation. Or this is the dispersion of data that you have by using the theta u formula proposed by the Eurocode date. So this is a phenomenological model based on formula that may be or may not be reliable in your case. Just what I want to say is that the reliability of the model is not based on the mechanics, but mostly based on the empirical way in which the empirical formulation were defined for this model. So now let's see some exercises. And we can go to our other slide. Okay. In the previous okay, yeah, let me. Okay. Let's see some application with Opensees. So if we want to use these kind of models in Opensees, you have seen with my colleagues, with my colleague Cristoforo, that there are basically two families of users of Opensees: the TCL-based and Python-based. So Python is emerging recently, and I have to say that it's very convenient from the effort that you have to do in the case of you want pre and post process data. In the case in which you are using TCL, you may want to be supported by MATLAB. In the case of using Python, you have several libraries that allow you to start and finish your modeling, pre and post processing and analysis inside Python, as we will see. For the TCL users, but this is also good for the Python users, there is with this nice page, maybe Christopher has shown you, that is called Opensees Wiki, in which you have a similar one for Opensees Pi documentation in Python, where you can see all the commands and features and utilities for these two programs. So this is a comparison between the two pages. The command manual page in Opensees Wiki and the model commands that are listed in the Python documentation website. So you can refer to one or to the other based on what is your experience. I also suggest for starting to start with some basic examples that are like the one that I'm showing you today. And I also gave you the files, so you can start with this example to make them more close to what you need to model. For example, in my case, when I started using Opensees, it was very useful for me to getting more confident with the software by downloading some reference example. Okay. As you can see, as also Christopher said, in order to generate an Opensees model, we have to define the domain, and the domain is made from the nodes definition, the element definition, the constraint definition, and the load definition. So we will see that after defining the relevant variables that can be geometrical or mechanical, we will define the nodal coordinates, we will define the constraints, we will define the material model and the properties of the material. We will define the cross-section of the elements and the elements itself. So defining the connectivity from this node to this node by using this element, and this element is made of this cross-section, and this cross-section is made of this material. In the case, of course, we have defined loads, and in the case of dynamic analysis, we have to define also masses, but you will face the issues of the masses definition and the dynamic analysis tomorrow with Dr. Sberna. And the recorder's concept, as also Christopher said, has a little changed by moving from TCOL to Opensees Pi. But by the way, you have to set what you want to monitor during the analysis. For example, I want to monitor this displacement, this reaction force, this internal force, or this deformation. You have to ask the program, what are the data that you have to store to be usable, to be visualized? And at the end, the kind of analysis, static analysis, monotonic or cyclic analysis, or time history analysis. For the TCOL users, as I think also Christopher said, you recall the analysis files by typing source, the name of the file that you want to run, .tcl. If you are in Python environment, you have to recall the libraries, and you have to have previously defined these libraries. The first is Opensees PI. This recall Opensees inside Python. This is very important because without this, you will not have Opensees in your Python file. Then OPS this, that is a very nice visualizer library, visualization library that you have in Python and you don't have in Tcl. This allows you to visualize your model, visualize the nodes, where are the nodes, visualize the number of the elements, the deformed shape, and the internal force diagrams also. Finally, the matplotlib library, they are important to have some easy and powerful commands to provide instantaneous diagrams that we want to do with the parameters that we are recording. For example, if we want to do a force displacement diagram, I ask during the analysis to record the force, record the displacement, and then through a matplotlib, I can immediately represent this in a very easy way. I suggest you, but this is my way of thinking, to separate the geometry models from the analysis models, okay? So in this way, you can have many geometry files. If you want, if I want to do a pushover analysis or a nonlinear static analysis of a structure or another structure, I can just change the geometry file, but using the same analysis file. So in my suggestion is to try to keep separate the analysis file and the geometry file. If you want to recall a geometry file or a call inside the, and you're a Tcl user, you just type source and the name of the file .tcl. If you are in Python, so this is Python, you just use the command import. Import and the name of the file without any extension. Okay, let's see some commands that we will see today. One of the commands is called =dof. That is important for defining the connectivity between the nodes that I'm using to provide a relationship between moment and rotation, or between force and displacement. Some material, the uniaxial material, we are using this very easy in elastic material, elastic perfectly plastic material. So it's an elastic material to which we can assign a yielding threshold, and this material moves as a perfectly plastic material after yielding. The min-max materials that you use to limit the deformation of another material, these materials are called wrappers. So let's say that after a certain displacement or after a certain deformation, I want that, for example, at this value of displacement, du, this element collapses. I have to use a min-max materials. So for example, materials that provide some boundary limits for the deformation, and after setting this boundary limit from the deformation, it can nicely simulate collapses. This can be a collapse of the hinge, for example, but this is very nice. But when this is applied to the fibers of a fibers cross-section, you can simulate the collapse of the fibers one by one. And this is nicely accounts for the softening of concrete materials, for example, as we will see. The zero-length elements that I use to connect the degree of freedom that has been released between the nodes. And then some concept of geometric transformation. The geometric transformation are basically, there are three: the linear, the p delta to account p delta effect, and the co-rotational transformation that we are using in the case we want to do large displacement analysis. And we will see how to do a monotonic incremental dynamic analysis. Okay. First, I introduce the exercise. I will tell something. Then, if you like, you can try to start to define it in Python. Okay, this is the case of a column having a axial load of that can have different values, like 400 kilonewton, 800 kilonewtons, and in the third case, 1,200 kilonewton. To this column is applied a lateral force, so the vertical load is fixed. The lateral force is monotonically increasing. The length of the column is 5 meters, and this is the definition of the cross section. These are the material parameters. This is basically a reinforced concrete element. As I told you before, in order to set and to define a moment rotation relationship for the degree of freedom of rotational degree of freedom, I have to start before with a moment curvature analysis of the cross section. I can do a moment curvature analysis of the cross section with, for example, still with Opensees, but you can do with any other programs that can do, for example, SAP 2000 is providing moment curvature analysis of the cross section. So you don't need to go by using Opensees. So if you perform the moment curvature analysis of this cross section by different level of axial force, you will see that as you can expect, that the more you increase the axial load, there is I think there is an error of the colors here. The red one is the 1,200. You can see that by increasing the axial force, you will increase the resistance, but you will lose in terms of rotation capacity. And these are the results of our moment curvature analysis at the different levels of the cross section that we did for preliminary did for this. Then we say that we want to convert this moment curvature diagram into a moment rotation diagram. And this is an example of using Excel files in which we compute theta u, theta y, and the plastic hinge length for the different level of the axial forces. You basically, what you can see is that the phi u and phi y values are changing. So we are obtaining that also the theta u is reducing with the axial force. Okay. Okay. Let's see how to model this in Opensees. We have to define if I step and use this microphone. You can hear me or not? No, not. Okay, this works also online. Okay. Okay, what we are looking for is this relationship here that define our nonlinear relationship between the rotational degree of freedom of these two nodes. With the zero length command, we define basically this relationship between these two nodes that are here represented as separate nodes, just for visualization matter, but they are in the same position. And the spring will account for the inelastic behavior in the degree of freedom tree. How we can prepare these in Opensees for defining the way of this node should work together. We are using the equal_dov command. The equal_dov command, so we first realize an hinge. We first realize an hinge through the equal_dov command. Okay, we first realize an hinge through the equal_dov command. And this is basic. And then in a second step, we assign the nonlinear relationship to the rotational degree of freedom. But at this stage, what we want at the beginning is that the node 1 and the node 11 should move together along direction 1, that this is the axis direction 1, and direction 2. While I'm not saying nothing about the rotation, it means that the rotation is free. So the syntax of equal_dov is okay. The syntax of equal_dov is node 1 and node 11 should move together along direction 1 and direction 2, and say nothing about rotation. So I will account the rotation between one node and the other node with a zero length element. For example, let's do some example here. Let's look at this example. In this example, I want to simulate a flexural plastic hinge, between node 1 in this for this structural system. Okay, if I want to simulate that by increasing this load, this cantilever can have some plastic rotation around this joint, I have to double the nodes, so define node 1 and node 11. So basically create an hinge, and then with a zero length element, create the nonlinear spring. So node 1 and node 11 should move together along direction 1 and direction 2. This is the hinge. Second, I define a zero length element. To this zero length element, I'm giving the tag number 2. I don't know why it's called 2. Okay, because the zero length 1 is this one. Okay, this is the tag of the element. And also this is the tag of the elements, just for each element that you define should be numbered by a tag, otherwise you get confused. So we are creating a relationship by setting a relation between node 1 and node 11 with the material number 2. So I have to define a material, a special material that I'm assigning to this zero length element. For example, let's say that this is the material, and along the direction 3. The direction 3 is the rotation. So let's try to look at this again. First of all, I create an inch, and I leave free the rotational degree of freedom. So I'm only saying is that these two nodes are constrained to move together along direction 1 and direction 2. So this is an inch. Second, I'm defining a relation that can be any relationship, linear, nonlinear, by defining the material number 2 to assign to between node 1 and node 11, node 1 and node 11 along the direction 3. And the direction 3 is the rotation direction. This is the syntax to create. In general, here is a moment rotation, but it can be also, as you can see here, a very general axial force relative displacement rotation. So in this case, for example, let's say that I want to simulate that when I reach a force level, this element is experience some plastic deformation. So I define a force displacement relationship that in this case is called material number 1. In this case, I'm setting an axial inch. This is an axial inch. I am using, I'm setting this between node 1 and node 11. They should move together along direction 2, that is sliding this direction, and direction 3, that is rotation, because this is axial. So I'm leaving free only the axial direction. And in fact, I have one here. So this means that in this case, this force displacement relationship is working along the axis of the element. This is just to remind that concentrated plasticity is not only about the hinges of the flexural hinges, but it can be any nonlinear relationship that can be used for linear or nonlinear relationship that can be used for to model some aspects in which the behavior of the element can change based on some condition. Okay. In the case we want to do this, because we said we gave information about the okay, we defined basically the definition of the hinge and the nonlinear spring, but we say that we have to define also a material model. Okay. In our case, we are presenting the elastic PP material. Elastic PP stands for elastic perfectly plastic material. This is a very nice material model that you can use for both representing stress strain response of force displacement or force displacement or force deformation. I mean that you can use it, for example, to be assigned in a fiber. And so in this case, it can work as a stress strain model, or you can use it as a concentrated plasticity. So you have moment and rotations, forces and displacement. So at a macroscopic scale, okay? This is just my example, but if you don't like elastic perfectly plastic material, or if you don't consider that elastic perfectly plastic material is good for your model, you have a very huge libraries of materials in Opensees. As you can see, these are some example of uniaxial material that I can use in Opensees. If you go to this link in the Opensees wiki, the list of uniaxial material is huge. We are starting with the elastic perfectly plastic material because it's the most simple nonlinear material. It is basically a material in which you have a elastic slope defined by this stiffness key, or in the case of we are dealing with a fiber, is basically this is the elastic modulus. And when the material is defined by a yielding strain or yielding deformation, the material works as a perfectly plastic. So no hardening material. So, and also we have no deformation limit. If we want to introduce some deformation limit, we should combine, we will see this in the next step, we should combine this with a min-max material model that is called wrapper. These kinds of materials are called wrapper because you wrap the main material with another material that limits the capabilities of the original material. Okay, so how this material works. So okay, the syntax here is described in TCOL, but in the example we have the converted one in Python. First, you give the material tag that can be 1, 2, or 3 based on the one you want. No, this is the strain limit. Sorry. So we define E for key, so elastic modulus and stiffness, and yielding strain or yielding deformation. In this case, we are assigning the yielding rotation. But I want to show that you see this in the code. So if you have a spider already installed, you can go to the exercise 1 and open this one. Okay, let's try to remember the geometry of our model. Is a column having 5,000 millimeters, so 5 meter height, it has a different way of defining the axial load. So I have several cases for the axial load. This is 400 by 500 cross section. So this is 5,000. Okay. Okay. You can see here that we are defining there is some delay. This is not the correct file. Open in the concentrated plasticity exercise 1, sorry. Okay. Okay, these are the geometric data. We are assigning the variable 400,000. We are defining node 1, as you can see here. We have node 1, node 11, and node 2. Okay. Remember that our plastic hinge will be assigned here. Okay, so we are giving the nodal coordinates 0, 0 to the node 1, again 0, 0 to node 11, and 0, the length of the column, L. So the constraint condition, the boundary condition to the node 1, that is the one at the base, is 1, 1, 1. It means that we are realizing a fix. And then we are defining basically the parameters of the elastic, perfectly plastic material. So this is the yielding moment, My. Theta y is the yielding rotation, and theta u is the ultimate rotation. As you can see, we have three different cases here. If you want to switch to case 2, you can use control 1 . By control 1, you can comment and uncomment the other. So when we want to move to case 1, from case 1 to case 2, I can comment and uncomment. So in this case, I'm analyzing the material for the case 2. But let's go back to the case 1. Let's go back to the case 1.
Can I interrupt? Why was it 11.1 for the first default?
Okay, yes. I'll show you. Okay, we did the moment curvature analysis for the cross section, and as you can see, we evaluate through this equation, but this is the case of reinforced concrete. For this cross section, what are the ultimate rotation and the yielding rotation. So I have pre-evaluated the limit state rotation for that cross section. I computed them in an Excel files, okay? Through these formulas that are in the Eurocode 8. But if you like using different way of computing theta u or theta y, or if the problem is another, you can do as you prefer. So in this case, as you can see, we are basically copy the data of this table here in terms of theta u, theta y, and the capacity in terms of ultimate moment here, my. You see in the first case, my is this one, 276.9, and we have again it here, 276. Okay, should be 0.9 maybe. Okay. So to the three different cases, I have three different moment rotation relationship, because the moment rotation relationship is influenced by the axial force. And I can define, if you remember, we need to define the stiffness to the uniaxial material. In our case, the stiffness is the ratio between the yielding moment and the yielding rotation. So if I do this ratio, my divided by theta y, what I can get is the stiffness. And this parameter is fundamental to get the to define the material. So as you can see, this is the way of defining in Python, in Opensees PI, in Opensees Python. OPS dot uniaxial material. Here we are recalling from the libraries the elastic, perfectly elastic material model. Okay. And we are giving the other difference with respect to TCL is that this string stays in the middle of between the brackets that are here highlighted as green, and you are using commas between the elements that you have inside the brackets. Okay. We are calling this material with a tag 11. If you go into the definition of the materials, there is the material tag, the stiffness, the deformation at which the yielding strain starts, the plastic behavior starts. You can give also a negative value, because if the material is symmetric, the materials can be symmetric or asymmetric. In this case, you define theta y and minus theta y. So the material is taking the key from this operation here, that is basically the ratio of my and theta y, and it is collecting these data here, and theta y is obtained from there. Okay. So I forgot to say before that here we have also defined the equal dot command. The equal dot command is basically that the node 1 and the node 11 should move together along direction 1 and direction 2, as we said before in the theory. So just comment this part of the min max material. Okay. Let's go to define the element. The element that we are using, I think you used this with Cristoforo before, is the elastic bin column. So we just call this element with the tag 1. This element is going from the node, is it? From node 11 to node 2, as you can see here from that. So from node 11 to node 2, we have the element having area b times h, and the moment of inertia is evaluated by the very well-known formula of the moment of inertia. And the trans tag is 1, meaning that we have a linear coordinate transformation, so we are not considering a large displacement assumption. So the last thing that we need at the moment, we have the element, we have the equal DOF, we have defined the material. Now we have to put the material into the zero length element that is actually our nonlinear rotational spring. So I'm calling this zero length element by recalling in the Python notation. The tag of the element is 2 to make it different with respect to the other elements. Because see here, element 1, element 2. If you set two elements with the same name, you will get some error message. And the material that I'm using, as you can see here, is the material 1. In our case, the material 1, yes, let's call this 1, material 1, in the direction 3. So it is exactly what we said in the description part of the slides, okay? Okay, just here we are giving the load, but this is not important because it is not affecting our analysis, but just to see if it works, we are setting minus P here to the node 2 to simulate the presence of the gravity loads or the vertical loads here. This is P. With minus P, because it's oriented in the vertical direction in a negative component, in the opposite ways with respect to the positive direction of the vertical axis, okay, let's cancel this, let's run this. You can see that this is the element that we create. Okay, this is the element that we create. The node 1 that you cannot see maybe the number. You can see the node 11, the node 2, and that we called with the red, the number 1 in red, we called 1 our element. Okay, this is the deformed shape in compression. You will not see very much deformation. And at the end, we have the moment and axial force diagram. Okay, as you can expect, you don't have moment diagram because we have an axial load only, but it is important to have a check about that if the model is working, and actually we have an axial force in the element that is exactly the 400 kilonewton that we are giving. If you like to increase these dimensions, for example, you set minus 2 to the scale of the diagram and run again the problem. Okay. Some of you was able to run the analysis. Okay. Very easy.
Where do we get the file?
Sorry,
How do we get the file?
the file?
Yeah.
Okay.
See the Zoom thing.
Zoom link. So if the one that uploaded the file can give some information, but I cannot see. So they are asking where they can get the.
Check.
Okay. So as you can see here in that folder, we have another file that is called push. That is the file that we are using to do the monotonic analysis. So the geometry file is ending here with basically doing the gravity analysis, and the gravity analysis is done in 10 steps. Okay. It applied the 400 kilonewton load in 10 steps of 40 kilonewton each. And this is the final diagram. Now we want to start from the end of this analysis to apply the lateral load and doing a basic pushover analysis. So we recall again the function of Opensees. It is always, and look at here, this is import x1. Here we are importing the file of the geometry that we have generated previously. And this is the same as attaching all the text that we have here from this exercise is attached at this point, okay? Okay, now we are defining a unit force. We will increment this unit lateral force that is applied at the node 2 along the degree of freedom 1, that is the horizontal degree of freedom. In the ops load, we are saying that the loaded node is the node number 2 with an horizontal force F, okay? We are giving displacement increments by 1 millimeters. If you like to reduce this, you can set 0.5. So if you have some convergence problem or you have waiting too much time to get the solution, you can decide to increase or reduce this increment of displacement, but it's basically this is the increment of displacement that you're giving to your analysis. And this is the maximum displacement that we want to reach. Okay. At the end, you can use this script always at the end. That is very nice to represent the output. So let's see if this works. Okay, we were lucky. This works. And this is our pushover curve. As you can see, we have. So first of all, let's cancel all the curves. Let's do the curves again. This is the static part, the gravity load part of the analysis. Then we are representing here the lateral pushover curve. And the lateral pushover curve is represented here through the capability also of Python and matplotlib libraries. In the case we were using Tcl, we were getting some text files that we should open with MATLAB or with Python itself or with Excel to represent this diagram. But what is very nice is in Python environment is that you can represent your response exactly in the same environment, okay? Okay, these are the bending moment diagram at the last stage. As you can see, look at these values. This is exactly the value of the plastic moment that we defined, because even at the last stage, the plastic moment is remaining constant, okay? And this is the shear. The shear that is coinciding to this value to which we have our final. So you were able to do this analysis. Some of you were able to do this analysis.
It's all done.
Okay, let's see that we want to simulate at a certain point that you see this material is this is our first nonlinear static analysis, but we know that materials have not unlimited deformation capacity. So let's say that at a certain point we want to simulate a collapse. Okay. So let's go again to the material model. Okay. Let's use this new. I want to show you this new material. You see at line 82, just uncomment line 82. I'm recalling this material that is called the Minimax. Minimax is a material, as I told you, that is defined to give some strain of deformation limitation to our curves. So if I'm setting this Minimax material, it works by creating a new material with a new tag to a previously defined material. So let's call 11, let's call 11 our previously defined material and put this 11. So the syntax is here. The tag of the min-max is 1. The tag is applied to material 11. Material 11 is the material that I have previously defined. Give minimum and maximum deformation capacity as the theta ultimate that I have defined from our moment curvature and then moment rotation analysis. So now I'm giving some strain limitation to my material. What I expect is that at a certain point, this curve will fall down, will drop, will have a drop. So let's see if first this works. And then you run this. So as you can see, we have simulated that at a certain point, we are simulating the collapse of the ball inflection. Very good. Oh, okay. If some of you did, it means that you should do it. Working. Okay, this is an example for a cantilever column, but imagine that you have a frame structure, and in this frame structure, you calibrate all the hinges. You can simulate all the progressive collapse of the hinges one by one. Very good. And this first example was working. We have time until 3 p.m. Okay, I will skip this example. That this is the previous example. Okay, if you want to obtain this other curve with this previous file, just uncomment and comment the different material resistance levels. Okay. Okay. Let's go directly to exercise number 3. That is a portal frame. Okay. In exercise number 3, we have that the column have different orientation. So we have a column that is in this direction, another column that is oriented in this direction, and a beam having 300 by 400 millimeters. The portal frame has a lateral force applied and a fixed 300 kilonewton applied at each of the columns. Okay. Again, to do this, since we are dealing with concentrated plasticity models, we have to calibrate the hinges. Calibrate the hinge means that for each of the cross section, I have 3 cross section. I have to perform the moment curvature analysis. As you can see, the beam having no axial force experiences the largest deformation capacity, while the column 1, which has axial force but also is offering the larger inertia, is having the larger resistance but lower deformation capacity, and intermediate behavior is offered by the column 2. So first I perform my moment curvature analysis. After the moment curvature analysis, I evaluate theta u and theta y for each of my theta u and theta y and the yielding moment for each of my hinges. So that's the way of modeling that I can adopt. Okay. In the more general case, in which I have 2 elements that are converging to a column, if I want to simulate that the plastic hinge can form here and also here, I have to divide the node in 3. So in this case, I'm using a node 3, node 33, node 333. While when I am connecting only one node, I'm having node 1 and node 11. Okay. In this case, that we know that to save some time, in this case, that since we know that the beam is resisting less than the other elements, we are not using this plastic hinge because we know that the plastic hinge will form here before then forming here. So in this case, this is not necessary. So I will describe you this model in its simplified version. That is this one. So let's see the code of this model. This is the results that we expect. So we expect to see that we reach a plastic capacity, and if we implement the min-max materials, we will see some drops that are associated to the failure of the column 1, column 2, and at the end of the beam until the complete failure of the elements. This is typical of concentrated plasticity. In concentrated plasticity, you have these sudden losses. It is not like fiber section elements in which you lose the elements fibers by fiber. So let's see the code and let's see the exercise number 2. Let's open exercise number 3, sorry, from the concentrated plasticity, exercise number 3. Open both the files. Let's open both the files. Okay. Okay. So as you can see, could you open the file? Open. Okay. Here you can see the geometric variables that are already defined. The geometric variable of the portal frame, the definition of the nodal coordinates. Okay. But as you can see, we have node 1, node 11, node 2, node 22. This duplication of the nodes, we are doing this to introduce the nonlinear springs in the middle. Okay. Node 3, node 33, node 4, node 44. Then the fix at the base of node 1 and node 2 of our portal. Then the definition of the equal dot. The equal dots are defined by node 1, node 11, node 2, node 22, node 3, node 33, and node 4, node 44, along direction 1 and 2. So we are leaving free the rotational direction 3. Okay, this is the definition of the material properties for the three cross-section. We have seen that we analyze the three cross-section. For each of the cross-section, we have M theta 1 and theta ultimate. And we are introducing each of them into a different elastic PP material. Okay. Column 1, the column 2, the beam with the same procedure that we use for the cantilever. Okay. Okay. Let's do like this. First, let's comment the min-max line. So comment line 87, comment line 101, comment line number 115. So let's call the material in 83 as 1, the material in 97 as 2, and the material in 111 as 3. Okay? Okay, the other part is simple. It is the definition of the element with the area. The element is an elastic element with the linear transformation. Then we are setting the zero length elements between node 1 and 11, node 2 and 22, node 3 and 33, node 4 and 44 along the direction 3. And this will perform the gravity analysis. Then we are setting a force at the node 3. The node 3 is the node, is basically this node here. Yeah, this is the node 3. You can see from here. Okay, 3 and 33. Then let's run the analysis. Okay. You can see the deformed shape. From the deformed shape, you can see something that is relevant to see. Yes, you can see that there is a the rotation is concentrated here and here. But since we removed I asked you to remove the min-max material, we can see that the curve is totally flat. Someone was able to run this analysis? Okay. Okay, we removed the min-max material, but now we want to simulate the collapse of the element. So let's reintroduce the min-max material. Okay, so to reintroduce the min-max material, go to uncomment line 87, uncomment line 101, uncomment line 115, and then let's call 11 the material in line 83, 22 the material in line 97, and 33 the material in line 111. And let's run the analysis again. And in this case, you can see that the element is experienced the collapse of the columns and then of the beam at the end of each stage. So this is very important because when we use materials with unlimited deformation capacity, we can risk to overestimate the plastic deformation capacity. So of course, there are no limitation of using this kind of approach. As we have seen, we can also use this in combination with shear spring. And in this case, we can also simulate potential collapse that is occurred before of the flexural one. Then with this, we have 10 minutes for questions or for helping you in your code. Questions?
Hello, I have a question. Am I audible? Hello?
Yeah, I can hear you.
Yeah, so so the question is, if I want to perform a combined analysis like with a factor with dead load, then another factor, I mean load factor with live load, another load factor with seismic load, all together in a combination. If I want to do a analysis, then how should I proceed? Just for a static analysis, if I want to do.
If I understood well, the question is assigning the vertical or the gravity loads and the vertical loads, and then proceed with the lateral pushover analysis.
Mm-hmm.
Okay, but it
Like
is already,
if you see in general, when we try to design something, we prepare load combinations, right? So if I is it a case that I have to analyze the structure separately for different load cases, or I can define the load cases separately before and call them in a analysis and perform the analysis for all the three load cases all together?
okay, this is mostly related to parametric analysis. So in this case, you have to program that your model, you set the load combination as a variables, and you perform a parametric analysis by running the analysis with a different load combination in series. Otherwise, you can run one by one. But it is something that is mostly related to the, how can I say, the way of doing a parametrization of the analysis. It is
Okay.
basically running what we did now for multiple times by setting, for example, a for cycle for running more times your analysis. This is not difficult, but we will see something about parametrization of analysis tomorrow,
Okay.
which you can, for example, parameterize loads, parameterize geometries, or parameterize other parameters.
Okay.
Thank you.
Sorry, another question.
Yes.
If I create a certain nodes and I do not connect those nodes with any elements or any definition, I have seen that the analysis doesn't converge. So is it a case that all the nodes should be connected? There should not be any free nodes?
Okay, you're referring to this slide?
Yeah, let's suppose I need 4 number of nodes, right? Or maybe 1 2 3 4 5 6 7 8 9 10 number of nodes. So if I create by mistake or while creating nodes some additional nodes which are not connected through equal DOF or zero length element or anything, I have seen that the model doesn't converge. It provides some errors. So is it a case
Okay.
that I should not create any free nodes?
Okay, this depends on the possibility that you have some disconnection, and you have stiffness matrix singularities based on your connection. But with Opensees PI, it is very nice to have the visualization of the nodes. I'm showing this now. So with respect to, for example, TICO, here you can see the node that you create, but it is important that even if you create the nodes, the structure is not unstable. So if you have instabilities, for sure the analysis cannot converge. So if you have some convergence problem related to this, it's because something is not, for sure, something is not connected properly.
Okay.
Okay.
Thank you.
Yeah.
I read reading questions by Jordan Stevie. No, yes. Yes, the flat slide, but okay, I use the flat slider also, but mostly this kind of element is used as for dynamic analysis to simulate something.
Right.
Or for
Yes,
example,
yes.
yes, you can use the flat slider. If I remember well, is something that can be used as a zero length element.
So only show at the very end.
And so, yes,
Oh.
this, we can definitely use the flat slider element inside zero length definition and zero length material.
Oh, okay. It would. Thank you so much. Yeah, that'd be great.
Another question. Is
Yes.
it possible to perform moving load analysis in Opensees?
Sorry, it is possible.
Is it possible to moving load analysis, like for live load analysis using influence line in Opensees? Am I properly audible? I will type in.
If you write, because the volume of the voice is a little low, so if you write, we can understand.
Yeah,
better.
yeah.
About the flat slider, okay, you can use both in static or dynamic analysis, but these kind of elements are typically used to model like isolators. So and because of these, in my experience, when I use with dynamic analysis, but for sure you can use also this analysis as a concentrated element.
Do you remember the name of the guy that we had the volume?
No, he's writing. He's
Okay.
writing.
Now it's better. Maybe.
Should write a question.
I have added my question there.
Yeah. Okay. Can you please a little bit more? Let's try maybe now it's working. You can repeat it now. You finish presentation. Because before.
Moving analysis in Opensees.
Excuse me, I have a question.
Okay, because we can stop.
Well, hello.
Hello.
Oh, I have a question. Yeah. When building the model, if there are both canary cable element and beam column element in the model, both at the same time, how to deal with the connection problem of the two to solve the problem of mismatch of the degrees of the freedom and to ensure that the deformation is coordinated and the connection point.
I understand.
Okay. We can't hear you very well. So maybe it is if you write, if we can read the question and answer. Okay.
Okay.
Thank you. Okay, about the moving load, I think that we don't have already done library for the moving
No, there
load.
is no
So
library for.
you have to program
Yes, it will be.
how to do this. So it's up on your more program capability. So you can do everything, but there is no already
like they can use
okay,
library,
you can use.
but there is an SDK.
What is the library function name for moving load analysis?
No, there is no.
There is no library
Okay.
for moving load. You should program this.
Okay, so I need to define the loads with respect to the distances and then run at different distances, multiple cases, something like that.
Yeah, you have to remove it each time. You have to remove the pattern. There is a remove pattern command in Opensees Spy. So you have to create the pattern, run, remove, move, declare another load pattern, and do it again.
Okay, so it's like I have to create a loop.
Yeah.
Okay, about parametric modeling, I think that some of the questions that
I am asking, it will be resolved. Okay.
yes,
Okay.
we'll say something about
Tomorrow
its
there is a lecture.
hysteretic loop. We will see something about cyclic loading at the end of the next lecture. We will show how to do a cyclic analysis. So basically, we will see nonlinear monotonic analysis and the cyclic analysis that you can use, for example, for obtaining this hysteretic loop. For example, to see what is the behavior before doing your nonlinear analysis.
For this one, there is the one you have to ask Massimo.
Okay.
Massimo develop element for
Yes,
connecting.
I would suggest to ask the question about the catenary element, cable element to Dr. Petracca tomorrow, who is very expert with this problem.
He developed a code for running.
Yes,
For
yes.
connecting elements with the different degrees of freedom.
Okay, when you run about Supriya question, when you run the analysis, you already have the gravity loads. They are not cancelled since you are running after a seismic analysis. So the gravity loads is considered in your seismic analysis. You are the analysis we are doing Opensees, they are sequential, unless we cancel the load effect. But when we run a series of analyses, like for example a gravity analysis and then a pushover analysis, the gravity loads or the vertical loads that we are explicitly considering, they are taking into account in the subsequent analysis. So the effects are combined.
You freeze them with time series 0. You do the gravity analysis, you freeze with time series 0, and then apply the incremental load.
At the end of the gravity analysis, or you can see that we have the time series as 0. It's also clear.
I don't know. I think in EX3. Here.
Load const. You see? This parameter will save the results of the gravity analysis. So
and freeze them.
And freeze them. Okay.
Okay.
Of the gravity analysis. So they are not cancelled after
So
you
it is already considering.
Yes, you are considering.
Yeah, you analyze, you freeze them, and you don't increment after that. And then you can run the incremental loads analysis, incremental displacement, all the stuff that you want.
Okay.
Okay. Let's have last 5 minutes breaks, then we will start with the second part of the lecture.
Sir, what about my question? My question was related to parametric modeling of composite structures in Opensees, like FRP reinforced concrete or tube-in-tube structure with infill RCC.
Okay, for parametric analysis tomorrow morning, the second lecture of tomorrow morning is focused on that. Okay. So Professor De Martino will show you how to run parametric analysis and how to run model updates, how to create models that you can use for model updating. And for composite structure, that is a specific question. Maybe you can ask tomorrow to Professor De Martino. Is the second lecture of tomorrow morning, right? Here, China time.
Thank you, sir.
Okay?
Yeah.
He'll show you how to run parametric analysis. So maybe a couple of your initial doubts can be solved by him from his lecture, and then you can ask if you have specific questions that are not answered.
Okay, sir. Thank you, sir.
Okay.
Yeah. Thank you.
No problem.
Yeah, I'm getting them. Yeah. So I didn't really understand why this is why this is. It's on the orientation of the. Yeah. Right? Yes. It's, you know, for to be, yeah, it's never done. Okay. You have these even words, right? You have the word of the process, and the word of the moment. Where you have changed different formulas. You declare how these cross sections are in the word of the cross section have y and z, and x is like outside the plane of the section, right? Y. If x is every time is along the direction of the okay? So we have x like this. That we have along the direction where it's like okay? Yeah. The rule between y and z, okay? How do you use to declare the reverse the vector get and then the plane okay, you're in the plane wisely, okay? Like this. Yeah. The direction of v in the global coordinates. Okay. So which the vector along v in the cross section that is along in the global coordinate system. In this case, in v is 1 0 0 is along x. Y, okay. Yeah. Oh, it's clear. Yeah. So in the plane YD of the cross section along V, can I use? Okay. Yeah, it makes perfect sense. So, yeah. So that's why. Like YD is okay. If I have X, we have X. Yeah. X is along the direction of the okay. How to manage this process with the system? Okay, you have the vector in the one zero plane, okay, local one along x. So this one along z. Okay. How this vector is oriented to the global one is here up here. In this case, 1 0 0 means that it's along x. Yeah, 0 0 y is the okay. So this vector here along v is toward x. Right? Yeah, I get it now. And this is 0 0 1. But is it always like that? Like how the professor? No. You can create the global coordinate system. You can set the global coordinate system. Of course, it should be consistent with the position of the. Yeah. You have to decide your global coordinate. The local one is so it's the y and z at 1 x along outside the plane of the cross section. Okay. Outside this way. Yeah. Now y is whatever. Y is the cross section. Yeah. How do you define the cross section? Okay. So now the problem is x is along the event. Okay. And what choose how to orient y and z. We have the effect of the y and z.
Hello? Can you hear me?
The global.
Okay, let's consider the second part of our theoretical presentation. In this is the second part. We will focus. Can you see also the shared screen online? Okay, so about distributed plasticity, that is very, very common approach. This is different from the previous one. because we are not working at the macroscopic level of a moment, curvature, or force displacement phenomenological relationship, but we are dealing directly with the stress strain response of the material of the fiber composing a cross section. I mean that if I'm able, this is basically the results of decomposing the cross sections into fibers and to assign to the fiber different behavior of the materials. In this kind of approach, we are mostly much more free with respect to the geometry of the cross section. So we can deal with any geometry of the cross section. Like, for example, in the case of that I've shown before, for example, of this formula here, these formula are formula that are developed for reinforced concrete cross section having a rectangular shape or circular shape. But what if my cross section has another shape? Also, in this way, I'm free with respect to the geometry of the cross section, and I also consider, for example, composite cross section. Composite cross section, I mean that there can be cross section made of steel and concrete, or in the case of the concrete, for example, here, I can decompose the cross section in the core concrete and cover concrete. Let's say that I want to take into account confinement effect. So the core of the concrete is included in the core. The core concrete has a much more strength and ductility because of the confinement, while the cover has less confinement. And then I want to give a different behavior to the rebars. Or, for example, I want to model, I don't know, a steel tube with some concrete inside. I want to model a reinforced concrete cross-section like this with a steel cross-section at the bottom. So I'm much more free with respect to the combining the geometry and the stress strain response of the material. So if before I was dealing with macroscopic relationship, now I'm working with microscopic relationship directly assigned to the materials. In the distributed plasticity approach, we will see that there is no need to predetermine the hinge position. I mean that if I forget to set an hinge somewhere in a frame in the concentrated concentrated plasticity approach, this hinge will not form. Instead, in the distributed plasticity approach, the element will automatically take into account the potential development of a plasticity. And this concept is totally disconnected with respect to the lumped plasticity concept. One interesting thing that we will see is that this approach is totally mechanically based. It means that it is sensitive to the variation of the axial force, and because of this, the neutral axis position is continuously updated during the analysis. So when I was showing you before the issue of the, what is it? The issue of the update of the axial force and to the problem that when I define a plastic hinge, the moment rotation relationship is blocked, is fixed, unless I define a multiple surface and the possibility to switch from a surface to another. With the distributed plasticity approach, this is automatically accounted. Okay. Opensees is not the only software that is dealing with distributed plasticity. We have other software, but basically the main difference that are not that are really relevant are these ones that I have already highlighted. Of course, I can select any uniaxial material to the different fibers, and by selecting, by doing this, I can realize a very, very complex composite cross-section and consider very complex behavior. Okay. Since we have 6 exercises, I will go very, very fast on the theoretical part, but we have some slides that will explain this in details. I think that mostly we can understand this from this slide. Actually, we consider the basic equation that we are using always to solve equilibrium problems and elasticity and plasticity problems that are based in the equilibrium equations, the compatibility equation, and the constitutive relationship of the material. Okay. The fiber section approach is based on the assumption of Euler-Bernoulli theory. So it means that the plane cross-section are the linear dependency between the strain in the deformed stage. So the fiber are respecting the planar cross-section hypothesis. Based on this, we can set some linear relationship between stresses and strains. Between the strains and their positions along the height of the cross-section. Okay. If you look at the equilibrium equations, they are the same equations that we can write when we approach to the equilibrium problem of the cross-section at the continuum level, but actually they are discretized into fibers. It means that if I want to set the equilibrium between the external axial force and the internal forces, the external axial force should be the sum of the stresses. If this is the one of the fibers, the I fibers, times its area, by summing all the sigma I times the I area of a fiber, I obtain the resulting of axial force. This is basically the translational equilibrium equation. And the same if I want to do the evaluation of the external moment. So I can write this relationship just considering the moment that is the force, the resulting force in the generic fiber times the distance with respect to the two axes, y and z. Okay. Then the planar deformation hypothesis basically states that the generic strain at the generic fibers can be obtained as epsilon 0, that it is the deformation in correspondence of the centroidal fiber, plus given to the linearity of the given the linearity, the linear assumption for the strains, it's basically zeta I, so the distance, for example, in this case, it's the y, sorry, times this angle that is the curvature, because in small displacements, the curvature times this distance will provide the strain capacity. So basically, in the case of XYY, this we can call this distance this distance here is yi, okay? So the strain epsilon xx is epsilon 0 plus this other part here, that it is yi, the distance, times k zeta. If I have double bending, so biaxial bending, I can set this also in the other direction, okay? Another important feature of this approach is that I can naturally account for biaxial bending. So it can happen, I can immediately solve problems of biaxial bending by writing, instead of translational equilibrium and only the rotational equilibrium along the moment, along the z-axis, I can set the equilibrium along z and y, and in this way I can solve also the p. Sorry, m z and m y, and this is directly accounted. Let's go to the stress-strain relationship. The stress-strain relationship of each fiber in the linear elastic case is E, the elastic modulus, times the generic epsilon, okay? In the case of nonlinear analysis, I'm considering a tangent elastic modulus or a secant elastic modulus. So the nonlinear behavior is accounted within these parameters, that is the elastic modulus. That is the parameter that is updated during the analysis because the material is getting into the nonlinear field. Okay, we have basically two kinds of elements. The fiber section based elements that is also called flexibility formulation, or the displacement based element, the stiffness formulation. These formulations are typically made, if you look, for example, to the very famous report of the Peer in Berkeley, where this formulation is very well detailed. In order to simplify the formulation of the elements, the rigid body modes are removed. So it means that if I have 6 degrees of freedom per node, if I have 6 degrees of freedom, say 3 degrees of freedom per node, by removing and just for the nonlinear part, for the flexural part, for the flexural nonlinear part, the translation, the rigid translation and rotation modes, I can reduce this system into this system in which I have as kinematic variables only the rotation of the node E1, the rotation of the node 2, and the axial deformation. This is basically the kinematics of the element without the rigid body modes. So by looking at the formulation of the theory of the fiber section element, of the force-based fiber section element, the main difference, I'm not going too much into detail, but the main difference from a standard formulation of finite elements is that in the commonly, when we develop theory of finite elements, we do approximation of the displacement field through the shape function. Instead, here the approximation that is not an approximation, is exact, is made at the level of the force. So basically, if I write the equilibrium equation for this cross section here, X, and I want to relate the internal forces to the external forces, and just doing a cross section here and write the equilibrium equation of these, also there is the assumption that in this case, I have two moments here, 1 year and 1 year. The moment is linear. So the moment is linear, it means that the shear is constant. So I can determine the shear as the sum of the moment divided by the L. So I can express the law of variation of the moment in this way, while the axial force is constant. And I can collect the relationship between the internal forces and the applied external forces by collecting all this term here that depends basically on the geometry of the element in a matrix that is basically the shape function matrix that is that not accounting like the classic shape function matrix. It's not interpolating the displacement, but is interpolating the force. Okay. Then for a cross section that is so defined, we can collect the section deformation. With the section deformation, this is the planar example to not making things more complicated. I'm not doing the generalized biaxial bending. Otherwise, it's also difficult to visualize. But what we are collecting the deformation of the cross sections that are epsilon 0, the axial deformation, and the curvature that are the dual deformation or our displacement theta, the rotation, and the axial displacement. We want to connect, we can connect the section deformations to the section force. And remember that the section force are connected to the external force, to the shape function that we defined already. In the linear elastic case, they are coupled by a section flexibility matrix. That's the reason why we call this a flexibility formulation, because we are working with the flexibility matrix. This is the dual of the stiffness formulation that is the typical of the, for example, we will see in the displacement-based approach. In the case in which we are in the nonlinear field, we are considering increments. We cannot consider total quantities because we are approximating the problem. So that in the nonlinear case, you see the dot, because this is increment of deformation is the tangent flexibility matrix times the increment of internal forces, okay? Well, we can obtain the flexibility matrix of the cross-section as the inverse of the stiffness matrix of the cross-section. And we can obtain the stiffness matrix of the cross-section by writing the equations that we have considered before. So basically, I set the equilibrium of the cross-section, I set the compatibility, and I set the constitutive model. Okay, so if I substitute the equation 2, this equation that expresses the linearity of the diagram, and the equation 3 into equation 1, it means that first I substitute this into this, and then I substitute this here. Okay, here you can see all the steps to get this. And then I collect some terms into a matrix. I have the internal forces on one side, the deformation on the other side, and what I have here is the stiffness matrix of the cross-section. Okay, this is the stiffness matrix of the cross-section by simply writing the equilibrium equation and substituting one by one. Okay. Of course, in the elastic case, the section, there is this stuff. Okay. In the elastic case, again, the section forces are connected to the section deformation truth. These are total quantities. In the nonlinear case, these are incremental quantities because I am again iterating during the analysis. Okay. So very simply, I can obtain with this relationship, I know how to determine the stiffness matrix. So by the application of the principle of virtual forces, what I want to say is that the nonlinearity of the matrix, so if some fibers are going into the nonlinear files, the stiffness matrix is updated and is updated to the tangent modulus of the materials, meaning that the materials, where is this? Okay, you see here, this sigma epsilon is the basic nonlinear stage that that provides the evolution of the tangent stiffness matrix, because when the material is elastic, we are here. But when the material is in the elastic stage, the second stiffness is different, and also the tangent stiffness is changing. So what is basically changing and what is basically updating the stiffness metric is the variation of this relationship here, or the update step by step of the relationship between stresses and strain through the variation of the tangent elastic modulus. Okay. To go at the level of the element, we can apply the principle of virtual forces. Remember, principle of virtual forces, instead of virtual displacements, we are giving increment of forces, okay? And by the arbitrarity of this term here, we can obtain the element flexibility matrix. The element flexibility matrix accounts for this flexibility that is the inverse of the stiffness of the different cross section. How this flexibility matrix is computed? The flexibility matrix is computed by solving this integral through the Gauss-Lobato numerical integration. The Gauss-Lobato numerical integration is basically considering a finite number of cross sections in the for these elements. Typical these elements are 5, okay, in which we know the values of the function, okay. These points are called Gauss-Lobato points or control section, okay? Since we know the relationship between stress and strains in this cross-section, we can reconduce this integral form to this sum of areas, basically some areas, in which WE are the Gauss-Lobato integration weights that are related to the tributary length associated to this Gauss-Lobato point, okay? What we are getting in this way? We are getting that the moment is linear, okay? We can also deal with distributed load but the distributed load are also reconduced to the nodes during the analysis. But with two nodes, since I know the relation between stresses and strain at the cross-section level, I can determine, for example, the curvature at this node here. So let's say that the blue curve is the real curvature. The approximation is possible. It is also a good approximation, depends on the number of Gauss-Lobato points that I'm considering. 5 Gauss-Lobato points are a good option for the force-based fiber section element. But what is important that I'm using 2 nodes, only 2 nodes to describe my problems. Instead, if I am using the older and the more similar to the classic finite element formulation, displacement-based formulation, I am approximation. The approximation is made on the stress field. So we are assuming that the axial deformation is constant and that the curvature is linear. But we actually know that the curvature is non-linear, is strongly non-linear when we have plasticity along the elements. So we cannot approximate curvature with a single element as we did for the force-based formulation. And so there is a dual formulation that we can develop for the displacement-based element, but the difference is basically the following. If I have a 2-node element, the moment is linear, but if I have some plasticity at the nodes, let's say that there are 2 plastic hinges that are forming, the curvature is starting increasing at the ends. Okay, so since I can approximate with a linearly the curvature, the trend of the curvature with a single element, there will be some relevant difference between the real trend of the curvature and the approximation of the solution. If I want to obtain the similar accuracy of that I obtained with displacement based the force-based approach, I should provide a refinement of the mesh. So in this way, I am approximating with linearly I'm approximating linearly the variation of the curvature. This is typically, it is typical to show in this example that is also experimentally obtained from Lehmann and Mehle test. This was a cyclic test on a scaled column over reinforced concrete pier, column pier, in which the experimental response, that is the blue one, is compared to the red one is compared to the analytical approximation. On the left, we have the force-based elements, and with one element at 5 integration points that are the one that we discussed earlier. Then the same obtained with the force displacement-based formulation with one element. Then you see that from one element to 4 elements, so we need 4 elements, at least 4 elements. It means 3 internal nodes and 2 at the side. It means 5 points to get the same accuracy that we had with respect to the force-based formulation. So this is the same results obtained with the displacement-based and force-based formulation. And so basically you can use both displacement-based or force-based, but remember that if your problem is related to the curvature, you need to refine that zones where you expect that you have the major nonlinearities, okay? So if you expect to have some strong nonlinearity here, so it is good to discretize more these regions. But increasing the number of points will increase the size of our problem. And because of this, if it's possible, we generally use force-based elements. Force-based elements have other problems that are, for example, with respect to taking into account gravity loads that can be taken into account. But okay, case by case, we can choose one or the other. For the most common application, the force-based approach is more convenient and practice to be used. There are also some hybrid elements. These hybrid elements are called beam with hinge. In this beam with hinge elements is a elastic element in the inner part. This is elastic part. And we have some finite length region in which we have fiber section formulation. So in this way, I can account for the plasticity only in this region, but the advantage is that I am including the axial force bending moment interaction, and I also consider biaxial problem in this case. Some people like this kind of element. I don't like very much, but okay, it is also an option. Maybe it can be faster in some cases with respect to the fiber section elements that are also computationally effective. So I think you waste more time in defining the plastic hinge length, but okay, it is also an option. As we said, for the concentrated plasticity, the shear problem is not directly accounted. So with concentrated plasticity, with distributed plasticity, with fiber section approach, we have not considering, for example, the possible formation of shear cracks in the elements. So this is not automatically accounted. So if I want to simulate this, I can combine the fiber section element with, for example, a concentrated plasticity hinge with a force relative displacement relationship that can simulate in case the failure in shear of the element. I would also say that there are some paper by Professor Spacone in which shear, the coupling between flexure and shear is introduced, but they are actually not implemented in Opensees. So there is some literature about the possible accounting of shear effect, shear failure with fiber section elements, in particular paper by Professor Spacone. But we have not already accounted in Opensees. So in conclusion, we can say that plastic hinge, by using distributed plasticity, we have not the need to predefine the position of the hinges, and so we don't need to calibrate. You remember that in the concentrated plasticity, we had those formula to calibrate theta u, theta y, and evaluate the yielding. So for each hinge, I have to define the moment rotation relationship. In this case, this is automatically accounted from the element. So we have an element that is able to account for basically the flexural capacity and also the deformation capacity. I can account axial force bending moment interaction. It means that if I have axial force variation on my elements, if I have some axial force variation on my element, the strength and deformation capacity of the element will be automatically updated because of the equilibrium, because we are step by step defining the equilibrium equation, and this will update the position of the neutral axis and again update the state of the cross-section. We are much more free with respect to the shape of the cross-section. We can account also biaxial problems. In this case, as in the concentrated plasticity, we say that the reliability depends on the reliability of the model that we use to calibrate the cross-section, the moment rotation curve. In this case, the reliability depends on the accuracy of the uniaxial stress strain models because we are working directly at the level of the fibers. This method requires more computational effort, but not too much more. So I think in most cases it's convenient. And finally, that shear issues are not accounted explicitly, but I can combine these with some concentrated plasticity approach. And then let's go to the other slides to show you some exercises. Okay. Okay, in my way of teaching this part, I usually start with a very simple case of a simply supported beam with a different constraint condition. Then we go to the fiber section reinforced concrete cross section with the rebars only on the bottom, monotonic analysis. Then we go to the column in compression, and then we go to the column in compression with some lateral force, and then column in compression with some cyclic force, and then with the frame. In my opinion, when you can handle monotonic pushover analysis, cyclic analysis, you can handle beam and column element, concentrated load and distributed load, you can simulate most of the structural engineering problems. Then the remaining part is up on your problem, or depends on your specific problems by changing the materials. But in general, this works for understanding how to combine things. So let's start introducing something by this simple example. This is a steel beam that we want to analyze we want to do a basically monotonic analysis in which we want to test this beam with a vertical lobe at the midspan and represent the reaction force versus the midspan deflection with Opensees. Okay. We want to see if there is some difference in the some differences that we can get by changing the constraining condition. So basically, okay, geometric variables. So we can go to open our files, so close the others, and let's open x1 from distributed plasticity, x1 and the push file. In the file, in the x1, we will see, let's cancel the previous diagrams. This is a beam with concentrated force. So we should divide the problems by adding an extra node here. So we will have, at the end, we will have node 1, node 2, and a node 3. Okay? This is the idealization of the problem. Otherwise, we cannot introduce the distributed loads. So in our variables, we have 0, 0, F of L, that is the midspan node, and 0, and L0, that is the final node. The constraints, we say that we want to test double condition of pin or fix. So, for example, we can start with pin condition, in which I'm setting 0 to the rotation. Okay? Okay. Now I'm defining the material with a still 0-2 model. Okay, here there are some, this is Python, this is TCL. We have the same in Python. So still 0-2 material is very common material used to model steel problems with keeping, in most cases, unaltered this parameter R0, C, R1, C, R1, capital C. These materials that also can account for the hardening can be used both for monotonic and cyclic response of steel, but both structural steels and also rebars. Okay, this is very easy material to be used. Okay, I just need to define the elastic modulus of the material, that for the steel is about 200,000 megapascal. Then I set a yielding strain, Fy, and then I set an hardening ratio. If the hardening ratio is 0, I go elastic, perfectly plastic, like the previous material that I was using, by setting a percentage of hardening, like for example 0.002, 0.005, I'm obtaining some hardening response. Okay, very important, by the way, is the definition of the fiber cross-section. Okay, the definition of the fiber cross-section, I suggest to define, for sake of simplicity, the dimension of the cross-section. So the base P and the 8H, okay? In this case, the 8 is 200 millimeters, the base is 100 millimeters. These two variables that are useful to define the coordinates of the points basically compute the health of B and the health of H, okay? Okay, then we recall the section operator, and in particular the fiber one, and this is the tag of the cross section. We are defining the cross section 1. Okay, about the patch. The patch is the way of that define the way of defining the shape of the cross section. There are different. Patch rect is basically for a rectangular cross section, but I can, for example, I may want to define some irregular shape cross section. For example, it can be the cross section defined with a generic shape, or for example, a circular radial problem like this one, for example, no? So if I want to simulate a cross section like this, I cannot go with the patch rect. So there are other, if you go into the libraries of the possible patch that I can use to create the cross section, based on your problem, you can use this. This is good for the rectangular cross section that are mostly common. Okay, you remember that I defined the material tag 1 to the steel. The cross-section tag 1 to this cross-section, we are assigned the cross-section that is defined with a rectangular patch made of material 1, and these other two numbers are the number of subdivision along X and along Z. For example, I can decide if my cross-section is very tall and has a very short base, and I'm doing a uniaxial bending problem, I don't need to discretize along the depth of the thickness of the beam, but only along the height. So for reducing the computational effort, for example, if I have bending only along y-axis, let's say that I have bending along only this axis, I can reduce this number along y. I can also set 1. In this case, the cross-section is divided into stripes. And if I want, I can increase the number over the height. In the case in which I am facing a biaxial bending problem, it is good to have a proper discretization along X and along Y, okay? So it's to somehow upon you select how many subdivision in X and in Y. I suggest, for example, if you have 50 centimeter beam, consider, for example, to discretize in 20, so to maintain the cross-section to be not larger than 2-3 centimeters, the fibers height. And so based on this number, try to, on this dimension, try to find the right way of discretizing along X and along Y. Okay, so first we say that this is referred to the way of patching. Second, the material that I'm using from the cross-section, number of discretization along Z and along Y, then the way of defining the geometry. Okay, the cross-section is defined around its centroid by these 2 points, point I, point J. With the patch rect, if I give the coordinates of the point I and then of the point J, it will construct a rectangle passing around these 2 nodes, okay? So first I give the coordinates of this node, then I give the coordinates of this node, and in this case, based on this positioning of the in the case that you have there, based on this positioning of the reference system, a local reference system, we give first the z coordinate. So if I want to define the coordinate of the point I are minus z, this is minus z, sorry for the multicolor, minus z minus y. Okay, and you said minus z1 minus, sorry, remember that y1 and z1 are, we are calling these z1 and calling this y1. Okay. So by doing this, we are saying that minus z1 minus y1 are the coordinates of point I. Then if I want the coordinates of point J, these coordinates are z1 y1, z1 y1. So now I finish it because I know that the cross section is made from a rectangular page. I defined the material. I defined the subdivision along Z and Y. I defined these 2 points. The cross section is entirely defined. Okay. Let's go ahead. Okay, this is the definition of the geometric transformation. The geometric transformation, we assume linear. We are not considering now a large displacement problem. We are using now the definition of the fiber section element. This is called nonlinear beam column or force beam column in Opensees. It seems that nonlinear beam column or force beam columns are almost the same elements. Maybe Massimo Petracca can explain the difference, but if you use nonlinear beam column or force beam columns, they work as distributed plasticity force-based elements. Instead, if you use the displacement beam column element, it is the displacement-based formulation that you have to care about the meshing, okay? The mesh size. This is the number of the integration points that you are defining along the element. So to our problems that we define at 3 nodes, node 1, node 2, and node 3, we have to define 2 elements, one going from node 1 to node 2, and the other elements from node 2 to node 3. So you can see that we define with the first number, the number of the elements, the tag of the elements, element 1, element 2. The element 1 goes from node 1 to node 2 with 5 integration points. And is made, this is the section tag, is made with the tag of the cross-section that is assigned to this element is this cross-section that I have defined before. But let's say if I want that the element 1 has the cross-section 1 and element 2 has the cross-section 2, I just need to define another cross-section that I can call cross-section 2. And in this way, I can change the cross-section of the element. In this case, we are using the same cross-section for both the elements. And finally, the element transformation. So we are using linear transformation. So that's the way of defining a force displacement elements, force displacement beam column element. Recall the element, tag, initial node, final node, number of integration points, section tag, and the transformation tag. Okay. Okay. Okay, this is a typical example that I do. Okay, the other things we already seen, we are putting a vertical load to test if this works. We can see in our example, by putting a trial load of 1 Newton, we see if we get the correct solution. And as you can see, for example, the shear is consistent because we have 0.5 and 0.5, while the moment here is scaled in a strange way. Yes. Let me see. Okay. Is 2000. Okay, don't look at the scale of the moment, so because we are scaling the magnitude from here, but it multiplies the value. Okay. So you see that the moment is linear, as we expect. It has a maximum point at the inner part, at the midspan, and we have a jump here. To control our solution, I use to do always, since this is a very simple case, we can, from the plasticity theory, obtain the expected lateral load. The plastic moment here is the resisting modulus times the yielding strength of steel. The resisting modulus for the square cross section is BH to the second power divided by 4 times to the yielding strain of stiffness. We get that the plastic moment for this cross section is 235 kilonewton per meter. Then by applying the kinematic theorem, the basic plasticity, we get that by the virtual work principle, alpha p times this displacement is the same of the work of the internal hinges. So we get that this is 4 mp divided by L. This is 115.5 kilonewton. So if we will do this analysis properly, we should get more or less this result. Let's see if we get this result. Okay, of course, here we are not considering hardening, so we should put 0 or a very slow hardening. Otherwise, you will get this is done in the assumption of elastic, perfectly plastic response. So let's go to see the push file. In the push files, we are considering the degree of freedom 2, so the vertical one, or the node 2, that is the central node. We are assigned the force into the central node. We are setting a maximum displacement of 500 millimeters with an incremental displacement of 0.5. We have minus because the displacement is opposite to the positive verse. Okay, and here we ask to do the analysis and plot the diagrams and plot the, if you look at here, we are collecting minus the displacement of the node 2 and minus because the displacement is negative. So we apply minus here, okay? The reaction instead at the supports are positive. So we are summing the reaction at node 1, and at node 3, this should be node 3. Sorry. Direction 2. Direction 2. So let's see if this works. Okay. As we expect, this is a steel beam, so it is deflecting. This is the deflection of the beam. Here in this case, you can see also the deformed shape of the beam. There is interpolation of post-interpolation of the displacement that is provided not by the element but by the Opensees visualizer. So we can see also the curvature of the beam. Okay. And this is the moment at the last stage and the shear at the last stage. Okay. But what's interesting is that we were estimating a maximum load by this simple calculation of 115 kilonewton, and it is very useful to have some control on the results we get. So actually we have 150 here. Then we set some small hardening, and because of this, this slope is still increasing. This is just the hardening. You can ask me why I'm not completely removing the hardening, because if I do set the hardening to 0, we can have some problems in solving the iteration, but we can see if it works. You see, the reason is that we have a 0 slope and we have some instability in the stiffness matrix. So the Newton-Raphson solution is not properly, is having problem to be solved. So my suggestion is give always a little bit of hardening in these cases in which you can have an element that can go to horizontal slope. Okay, so, and this was the case of a simply supported beam. If I, for example, put a fix condition, I'm just changing the constraints into fixes. You can see that the deformed shape is changing because now this constraint is a fix. So you have horizontal tangent here. Okay, you have horizontal tangent here. And the resistance is increased. Is increased because I am using 1, 2, 3 plastic hinges. So the resistance here is double than the one of before, because if you compute this, it's about 230. Because if you compute this from the plasticity, you have to consider both the hinges at the other sides that do half of the displacement of the central hinge. Okay, this is just for to confirm that our results are good. So when we are predicting something, it is good to do some simple calculation to be sure about the results. Then when we are sure about the results, we can do more complex things. But let's go to this very interesting case of reinforced concrete beam. Okay. Okay. Again, this is the same beam, but this time we have 250 by 500 millimeter cross section, and we have 516. 516 means in 1.6 centimeter is the diameter. And again, we want to do a analysis by plotting the vertical, the deflection at the midspan and the sum of the reaction. I want to show the difference with respect to the reinforced concrete to the steel beam. Okay. Look at this condition. We will analyze this. In this case, this is a slider, and this is a double pin. So this is not sliding. We will see that when we are using fiber section element, we should be conscious also on the boundary conditions. Because there is an interaction between the force and the bending moment. Okay, I will explain you better from the experience. So first, I want to introduce this new material. Let's introduce directly in Python. This is called concrete 02 material. We have also concrete 01. The concrete 01 has no tension, and it has also a very simple hysteretic rule. It's a very common material, but if you look at the Opensees libraries, you can see that you have, I would say, at least 10 or more kinds of concrete materials. This kind of material is defined in this way. Okay, first I have to set the tag for the material. Then this material is defined by these 2 points, by giving the coordinates of these 2 points. And these 2 points are the peak stress and peak strain. So in this case, minus 30, minus is because we are in compression. So we are setting minus 30 megapascal, and minus 0.2, minus 0.002, that's the peak strain. I can do my stress strain analysis of the cross section if I want to include confinement or not. Then I'm setting an ultimate strength and ultimate deformation. After that point, my material is going constant. Okay. We will also see that we can use also some wrapper like min-max to simulate the failure of concrete in compression. Other parameters here are the tensile resistance of concrete, and these are the parameter here that accounts for the softening modulus. This is basically regulated from the fracture energy. Okay. Okay, we have already seen how to define fiber cross section, but I want to tell you something about how to put some rebars in a cross section. So the rebars in a cross section can be put in different ways. We can have some point, define some points where we set some rebars, but in the case of a rectangular cross section like this one, it is very useful this command that is called the layer straight. In this layer straight, I define 2 points the point I and the point J. So along the coordinates of these 2 points, I can select the number of rebars that I want and the diameters of the rebars. And these rebars are equally spaced along the coordinates in between these 2 points, okay? So okay, we are here, sorry. In Python, in Opensees PI, this is the material tag. Material tag means that I have to use the steel. Let's open also, it means that I am considering where is the steel here. Somewhere I have defined the steel. I'm setting the steel 02 material as 3. The second number here is the number of rebar. At the beginning, I said that the layer option is straight. Then I set the coordinates of this number, of this point, and then of this point. With respect to this axis system, after defining the variables zeta1 and minus zeta1, this point here, with respect to this reference system, this point here has coordinates minus z1 plus cover and minus 1, 1 plus cover. This point again, minus z1 plus cover, and then 1, 1 minus cover, okay? For rebars, having material 3 and area of each rebar AS1, and the variable AS1 is defined here. Okay, let's see this into the code. Okay, let's close the exercise 1. Let's open the exercise 2 and see if it works. So this is exercise 2. That mostly I have shown you the main features of this exercise. Okay, let's start. Let's start with the pin slider condition. This is a test value of 1 kilonewton to see if the model is working. Again, we have that the shear diagram is consistent. The push file is exactly the same as before because the model is basically the same, only the cross section is changed and the element is changed. So if we run the analysis, Okay, let's do this. Meno funziona. Meno 0,2 meno 500. La posizione. Perché valore assoluto? Vediamo qualcosa. No, scendi giù. Così, questo cancelli tutto. Ok, sono cancellato tutto. Aspetta, lo stesso non si vede. No, no, è impazzato proprio. Di nuovo? Più grosso? Ecco, più di spider ya. È impazzito. No, no, senza bisogno di chiedere questo. Devi proprio di prendere lui. Devi fare. Come dici, ok. Ciao, non ci. Non so. Bene. No, questo è l'ex 2. Questo è l'ex 2. Questo c'è l'ex 2. Allora, quello si sta girando. No, pazzi, vai. Vai. Di nuovo. Basta. Il risultato non. No, sì, devi togliere il dico, almeno il dico. Sali, sali. Stai così. Ma non lo fa verso l'alto, mi sa. Lo spingere verso il basso. Era meno 500. Allora diventa il meno. Va? Ok. Sì. Okay, let's go directly to the solution of the fix beam. Okay. Okay, this is the fixed beam, and this should work. Okay, this is working. If I want to simulate the progressive collapse of the fibers, I can activate here the uniaxial material, setting this as 11, so the 11 is accounted into the dropper, and instead of this curve, we will face Okay, I will fix this and send you tomorrow to later. And let's move to the other exercise. That is a column compression. In this case, we are considering the case of core and concrete cover, because it is common in earthquake engineering problems that sometimes we want to have some different materials simulating the outer concrete that is unconfined, and the concrete inside the ties, inside the syrups, that considers the confinement effect. So in this case, I have to define two different types of concretes. And for the definition of this kind of cross-section, I have to define the cross-section with 5 rectangles. So these 5 rectangles are the core rectangular from point E and point J are red to red. Then I have these blue to blue, blue to blue horizontal rectangles, green to green, and green to green vertical rectangle. So let's open exercise 3, and let's hope that it works this time. Antonio, meanwhile, if you can check exercise 2, I will send you. Okay, Saint Antonio. Okay, so let's open exercise 3. Okay, hopefully it works. Okay, so let's see that we have two kinds of materials here that we have defined. One is the core concrete that is more resistance and more ductile. You can see this from these parameters. When we have the same steel, the steel material is number 3. Okay, then this is a column made of 2 points, as you can see, point 1 and point 2. The only special thing is that we are considering the confined and unconfined concrete. So we have a patch rect for the inner column and 4 patch rect that are the 4 rectangles that represent the unconfined cover. Okay. About the different layers of reinforcement, so you can see that we want to simulate 3 different layers of reinforcement. 1, 2, and 3. 1 with 4 rebars, the middle with 2 rebars, and the upper with 4 rebars again. Antonio, check if there is a 0 in the layer straight somewhere, because this creates problems in Python. 0, I mean 0 elements, 0 bars. Okay. So let's start with the analysis. So we get a diagram that is like this. That this is about 5,200, something like that. We can get these results as an estimation by accounting for, since the resistance of the concrete is 30 megapascal, okay, of the confined concrete. The unconfined concrete is 25 megapascal, and the resistance of steel is 450 megapascal. By multiplying, if I want to predict before the analysis what is the maximum capacity in compression of the column, in a very rough approximation is that all the materials reach the maximum resistance at the same strain value. This is not true because the cover is reaching the capacity before, then the core is reaching the capacity, then it's the steel in compression has different deformation, even in deformation, yielding deformation, even if it is similar to that of the concrete, okay? So I'm basically multiplying the resistance of the concrete by the inner area, the resistance of the outer concrete by the perimeter area, and the resistance of the rebars, of the steel rebars, by the area of the rebar by the number of the rebars. We have 10 rebars, 516, and one 516 has an area of 201 millimeters. If you sum this, you get 5,500. This should provide an overestimation because it is assumed that the materials are reaching the capacity at the same deformation level. But if you see, we are not so distant from the estimation. We have 5,200, 300 more or less. Okay. Let's see what happens if we add some min max material to the core and to the cover. So I am uncommenting lines 58 and 59. And I am setting material 1 as 11 and material 2 as 22. Okay, in this case, I can visualize the so this is a compression test. So the load is perfectly centered. So this first drop is occurring when I suddenly lose the cover concrete and I lose this resistance capacity. Then I'm losing the cover concrete. Then the model only see the rebars, but actually the rebars are going to buckle if I have no concrete inside. So if I put some strain limits to the rebars, I can see also the failure of the rebars. So actually, the first loss is about 1,400. The second loss is 3,000. The last loss is about 900. As you can see to somehow clearly from this, and you can see that what we estimated is to somehow reproduced by the model. Okay. Of course, in this case, again, I repeat again, you have no concrete. It's supposed that all the concrete is crushed. This is only the cage of steel, but the cage of steel cannot resist the gravity loads because it will buckle. But okay, you are not actually interested to see what happens here. So generally, I'm interested to lower the formation. What I want to show here is that if you want to model properly collapse, you have to deal with the min-max material. So let me some of you will do the analysis. Okay, this is without min-max material. Problems? Change. No. Change the because now this material should enter the site. Now you can see the Okay. Some of you have already faced the problems. Meanwhile, we are fixing as exercise 2. Qual era o problema? Maybe we have a solution for exercise 2. Io lo salvo per funzione. Qual è? Meno uno. Dovrebbe andare? Poi. Okay, very nice. Thanks, Antonio. Okay, this is the beam before. This is with min-max material. Min-max material. And this is with min-max material. Let's see if it works only also with the pin sliding condition. No, poggio carrello continua a non girare. Okay. Let's go to this example. You can consider this as a column scared column of a bridge pier subject to cyclic loads. Okay, so the only difference here is applying a cyclic load. That I want to show you how to apply cyclic loads in the distributed plasticity exercise number 5. Exercise number 5. Consider the cyclic 1 file. Okay. Just look at this file, that this is the one related to the cycles. Okay. In these files, we are basically defining the drift. The drift are the ratio between the displacement and the length of the element. So in this cyclic file, we just for convenience, we are setting the length of the column, this parameter L call, that is the length of the column, that is 5,000 millimeters, 5 meters. And we are by this vector, this array, we are giving a displacement, imposed displacement as a percentage of this length here. So it means that we are reaching drift that go on 1%, 2%, 4%, 2%, and again 5%. Okay. With this vector here, I can ask to do cycles, full cycles at the drift level that is collected, that is defined in this list. Okay. Cycle type is 2. I don't know why here, but you can select also the number of repetition of cycles that you can use. Okay. In
तो सुबह से नंबर दिया, 7:45 बजे कॉल किया, 8:45 ड्राइंग दिया, और मेल में क्या लिखा, सुबह तक बता दो मेरे को, तक बता दो, और तुम्हारा पेमेंट टर्म भी बता।
Hello? Hello? Can you hear me?
Hello? Yeah, now they see. Okay. Okay, the previous example, did you couldn't hear the voice for the previous example, this of the column? So you need that I explain this again, the column with cyclic load? exercise 6 is the new one. So I'm starting with exercise 6. So you need also for exercise 5 or not? Okay, exercise 5 is the I'm repeating very rapidly, is the example of a column, well, a fiber section column element with the imposed vertical load and cyclic loads file. So it is exactly the same column that we analyzed before with 2 nodes. So in this case, we have pushover analysis. In this case, we have cyclic analysis. And the cyclic analysis is the cyclic analysis is exercise 5. By opening these files, you can see the cyclic analysis file here. Okay, and this file basically contains a list of drifts, interstory drifts intended as the ratio between the lateral displacement and the height of the column, with this variable here that defines the length of the column. And our peaks are generated by multiplying this interstory drift ratio times the length of the columns, and each time this will provide a cycle having the maximum amplitude of, let's say in this case, 0.001 times 5,000. It means that the maximum displacement at the first would be 5 millimeters. Any problem? And so on. So if you try to run this model in its original version, let's uncomment first the min-max material model. You will see some cycles that now I have reported as interstory drifts because I'm dividing the displacement by the length, okay? I'm doing this here. I have just divided by the length of the columns, but if you remove these, you can visualize in terms of absolute displacement also, you can do another plot, okay? Okay, if you want to see also some significant degradation that is introduced by the min-max material, you can uncomment these lines here, 58 and 59, and set as 11 and 22 to the materials, so that these materials, 11 and 22, are the one included into the min-max materials that is called 1 and 2, and I can provide again the cyclic response of the column that, as you can see, has some convergency issues, but this is because they advances degradation of the material. So you can use these if you want to simulate that at a large displacement you lose the capability of the column. So last example of the day, then we will be here for some question. I can see that Professor Marano joined us. It's a long time that I don't see him. So let's go to the last exercise. This is a very simple portal frame. We have some lateral loads applied, P and 1.3 P, like to simulate a lateral distribution profile of forces. In this exercise, this is nothing special, just we are learning how to use the LL load. LL load is the command that we use to set a distributed load. and we have two different cross section, one for the beam and one for the column. We will do this exercise with and without the min-max to highlight also the different collapses of structural elements. So let's open directly this on Python. It is exercise 6. In exercise 6, yeah, you can see different variables, the variables, the geometric variables that set the dimension of interstories, the dimension of the portal, and the different position of the nodes. We have fixed at the base, two different concrete material, confined and unconfined, one steel material. Here we have hidden our min-max material that we will activate later, the definition of the cross-section, and actually the connectivity of the elements. That is very simple to understand. The definition of the loads that is applied to node 5, 6, 9, and 10, that are basically the nodes at the first and second story. Okay. Then if we define the geometry of this, if you look at the geometry of this portal frame, let's cancel this, so look at the geometry of this portal frame. You see that we have element 5, that is this beam, and element 6, that is the beam at the upper stories, that we want to load with a 30 kilonewton per meter load. 30 kilonewton per meter is the same as Newton per millimeter, so we don't have to change unit from kilonewton per meter and Newton and millimeters. So the command here is load, that is used to generate a distributed load, load L, two elements 5 and 6. The type of the load is beam uniform. There are, if you look inside the Opensees documentation, other shapes of giving the loads, triangular and so on. Okay, this is a simple uniform load of 30 kilonewton per millimeter. So let's go to the pushover analysis. The pushover analysis is nothing different with respect to what we have seen before. Just we have to set two nodes to push, node 5 and node 9. And we say that at the node 5, fx is 1.3p. And then let's see if this works. Okay, it is working, hopefully. So you can see the displacement shape of the portal in its ultimate condition. Okay, this is the gravity load analysis that you have from the gravity analysis. As you can see, that is consistent because we have a parabolic shape of the bending moment diagrams that is consistent with a uniform distributed load. This is the shear diagrams, and this is the pushover curve, okay, and the deformed shape. Again, if you like to see the degradation of the fibers when they reach the ultimate strain, you have to set the where is this? You have to set the min-max materials and call 11 and 22 the concrete material so that they can enter inside the min-max and are being referred to as element 1 and 2. So in this case, the pushover analysis will consider the degradation. We have some problems of convergence. Okay. Maybe 1.3p was too much, so let's start with PMP. We could not see some failure, so correct with using the same values of the lateral load, P and P. And as you can see, in the previous case, we had analysis that, okay, maybe it is good to run again the previous analysis by removing the, so they are comparable. Yes. Okay. This is without considering the min-max material, and this is with considering the mix-max material. So you can see that you can visualize clearly the softening. This is very important when you compare concentrated plasticity with lumped plasticity, distributed plasticity with concentrated plasticity approach, because in most cases in concentrated plasticity approach, you have some predefined limit like theta u. After that, you have the collapse, and in the distributed plasticity fiber section element, you have to define this at the fiber level. Otherwise, you will not see the collapse. That's why I'm stressing this many times during this course. So this was our last exercise. I think we finished almost in time, even if we had some delay. But we are here now for the answering some questions from online and in presence. Then the exercise for today could be try to add, for example, another story or to modify this into this. But before going into this more advanced exercise, I would like that everybody are at least able to run this one. And so I'm going around the room to answer your live problems. Okay.